Welcome to our second lecture on hypothesis testing. Let's get to work.
Now, traditionally, if you can recall from high school maths, we have to integrate the function of the curve in order to calculate the area underneath the curve. However, this is tedious and time-consuming. The normal distribution function is indeed rather complex. Instead, the areas underneath the normal distribution are all listed in a standardized table. That is, someone has already done all the integration for us. However, in reality, there are an infinite number of normal distributions. What do I mean by this? Well, many distributions can be normal. For example, we may observe a normal distribution that has a mean of 10 and a variance of 10. Or we may observe another normal distribution with a mean of 5 and a variance of 6. Or a normal distribution with a mean of 1 and a variance of 2. And so on. However, does this mean we must have an infinite number of normal distribution tables at the back of our textbook? No, obviously that would be too cumbersome. But on the other hand, integrating the normal distribution function is too tedious. So what to do? Luckily, we have one standardized normal distribution known as the Z-distribution. It has a mean of 0 and a variance of 1. All other distributions can be easily converted to the Z-distribution. As such, you only need the Z-distribution table, and your textbook does not need to weigh a ton with thousands of possible normal distribution tables. Okay, how does the standard normal distribution, or Z-distribution, look like? Well, Z, which tells us we're talking about the Z-distribution, follows a normal distribution with a mean of 0 and a variance and standard deviation of 1. So as we can see from the diagram, it is bell-shaped with an average of 0. So it is symmetrical around 0. Also, the area underneath the curve sums to 1. This is because the area underneath a probability density function represents probabilities, and probabilities must sum to 1. Let's go through some examples to make some sense out of this. Okay, so here's a Z-distribution with a mean of 0 and a standard deviation of 1. Now, what we mean by the cumulative Z-table is that it gives us the probability of observing a value of Z that is equal or less than a specific number. For example, what's the probability that Z is less than 0? Well, in this distribution, we're asking about the area underneath the curve when Z is less than 0, which is this area. Notice that it is just the area underneath the curve to the left of 0. Suppose instead I ask you what is the probability that Z is less than 1? First, we must find 1 along the x-axis, which must be on the right side of 0 as 1 is larger than 0. The probability that Z is less than 1 is simply this area to the left of 1. Now, what is the probability that Z is less than negative 0.5? Well, we must find negative 0.5 on the curve, which is on the left of 0 as it is a negative number. The probability we are after is the area underneath the curve that is to the left of negative 0.5. Alrighty, so now we know what we're looking for, the specific areas underneath the curve. But how do we calculate the areas underneath the curve? That is, how do we figure out the exact probabilities we're after? Simple. We use the Z-table. This is a cumulative Z-table, which gives us the cumulative probabilities. That is, the probability that Z is less than a specific number. There is another type of Z-table that you may have in your textbook. I'll cover this a little later. Okay, so how do we use this? Well, the first column refers to the first number and first decimal point of the Z value you're after. The first row refers to the second decimal place of your Z value. And the numbers inside the table are the cumulative probabilities. So back to our cumulative probability exercises. What is the cumulative probability of Z equals to 0? That is, what is the probability that Z is less than 0? Well, we look up 0.0 in the first column. The second decimal place is also 0, as we're looking at 0 exactly, not 0.01 or 0.02. So we look up 0 in the first row. These two values correspond to 0.5. So we now know that the probability that Z is less than 0 is 0.5. Now, this makes sense, as the Z distribution is symmetrical around 0. So 50% of the curve is less than 0. That is why the cumulative probability is 0.5. Half of the curve lies below Z equals to 0. Now, what is the probability that Z is less than 1? That is, what is a cumulative probability of Z equals to 1? Well, 1 is equals to 1.00. So in the first column, we look up 1.0, and along the top row, we look up 0. This corresponds to 0.84134. So the probability that z is less than 1 is equal to 0.84134. Okay, let's try one last example. What's the probability that z is less than 2.44? Well, first we look up 2.4 along the first column, and the second decimal place is 4. So we look up 4 in the second row. These two numbers correspond to 0.99266. This means that the probability that z is less than 2.44 is 0.99266. This means that over 99% of the z distribution is smaller than z equals to 2.44. There are two important rules you need to know when using the z distribution. First, the z distribution is symmetrical around 0. This is often referred to as a symmetry rule. So say we have the z distribution like so, with a mean of 0. Now, suppose you know that the probability that z is larger than 1.5 is equal to 7%. Now, due to the symmetry rule, this means that the probability that z is smaller than negative 1.5 is also equal to 7%. So the distribution is symmetrical around 0. It's like a mirror image reflected at 0. Let's look at another example of this rule. Suppose you know that the probability that z lies between 0 and 1.5 is equal to 43%. Now, again, because of the symmetry rule, we also know that the probability that z lies between negative 1.5 and 0 is also equal to 43%. The other rule is known as the complement rule. Basically, the area underneath the distribution must sum to 1. Recall that the area underneath a probability density function can be interpreted as probabilities. Well, the sum of probabilities for all possibilities must sum to 1. Let's draw out the z distribution. Now, again, suppose we know that the probability that z is larger than 1.5 is equal to 7%. Using the complement rule, the area underneath the curve to the left of this, that is, the probability that z is less than 1.5, must be equal to 93%. So the probability that z is less than 1.5 is equal to 1 minus the probability that z is larger than 1.5. 0.93 is equal to 1 minus 0.07. Are you guys still with me? The more practice we do, the more it will become second nature. Finally, I'd like to briefly talk about a different type of z-table commonly used in statistic courses. Not all z-tables provide cumulative probabilities, like the one we used a few slides ago. Now, recall that the cumulative probability tells us the probability that we observe a z-value that is below a particular number. In some other z-tables, they tell us the probability that a z-value lies between 0 and a particular number. The capital Z here denotes a specific value we're interested in. Let me show you what I mean. Okay, so suppose we're interested in the probability that z is less than 1. However, the z-table we're using only tells us the probability that z lies between 0 and 1, this blue shaded region. So what can we do if we want the cumulative probability? Well, remember the symmetry rule. This means that the curve is sliced perfectly in half through 0, and we also know that the area underneath the curve sums to 1. So we can deduce that the area to the left of 0 must be equal to 0.5. So since we know the area to the left of 0 is 0.5, and the z-table tells us the area between 0 and 1, we can sum them up and find the cumulative probability of z equals to 1. That is, what is the probability that z is less than 1? So we can calculate this by summing up the probability that z is between 0 and 1 and 0.5. Using the z-table, you'll find that the probability that z is between 0 and 1 is equal to 0.34134. Therefore, the cumulative probability is equal to 0.841, which is what we found earlier. Okay, so back to our example. So recall that the third step is drawing the distribution and the rejection region. Now, the tricky part here is figuring out the critical value, which is the cutoff value for the rejection region. Step 4 requires us to draw the same distribution along with its rejection region in the standard normal distribution space. That is, we want to convert our original distribution to a z distribution. Why do we do this? Because we know the size of the rejection region, in this case it's 5%. Since we know the size of the rejection region, we can use a Z-table to find out the critical value on the Z distribution. Once we know this, we can simply convert this value back to our original distribution. So we draw the Z distribution with a mean of 0. Remember, the mean is always 0 in the Z distribution. Now, for this example, we're dealing with a lower tailed test with a significance level of 5%. So we draw this in our Z distribution. The question, again, is what is the cutoff for the rejection region? We call this the Z critical value, denoted by ZC. Now, I'm not sure if you noticed, but our Z table only contains Z values that were positive. The Z critical value here is negative, as it's below 0. So we need to convert this to a positive number. It's quite easy actually, as a distribution is symmetrical around 0, then the area that contains the lowest 5% of the distribution is equal to the area containing the highest 5% of the distribution. Similarly, because the distribution is symmetrical around 0, the cutoff to the highest 5% of observations is simply the negative of the critical value we're interested in. Now, recall that we're dealing with a cumulative normal distribution. So the probabilities we observe in the Z-table relate to the area to the left of a particular Z value. So the area of the curve represented by the probability in the Z-table is this. Since we know our rejection region is 5% and that the area underneath the curve sums to 1, then the blue area must be equal to 95%. So how do we figure out what the negative of our critical value is? Easy. We look up 95% in our cumulative Z-table. So we open up our Z-table, and since the probabilities in the table are cumulative probabilities, that is, the area to the left of the Z value we're after, then we must look up 0.95. The first number I spot that is close to 0.95 is this one. However, 0.9495 is very close to what we're after also. Since 0.95 is pretty much perfectly in between these two numbers, we can simply take the average of the corresponding Z values. So what are the Z values? The row tells us that it's 1.6, and the columns tell us that the second decimal place is 4 and 5. So the Z values are 1.64 and 1.65. Taking the average of these two, we find that the negative critical value is equal to 1.645. Okay, so back to our distribution. We now know that the negative of our critical value is equal to 1.645, which cuts off at the top 5% of observations. And due to the symmetry rule, the critical value we're after must be equal to minus 1.645. Now, what does this mean? This tells us the cutoff of the rejection region. How do we interpret the Z critical value? It tells us how many standard errors away the rejection region is from the mean. Don't worry, I'll explain this in more detail shortly. Okay, in step 5, we calculate the critical value in the distribution of the sample mean, that is, the original distribution, not the Z distribution. Recall that our Z critical value is negative 1.645. This tells us that the critical value, or the rejection region, is 1.645 standard errors below the hypothesized mean. Because we have a negative Z value, it means that the cutoff for the rejection region is below the hypothesized mean. Now, you're probably asking yourself, what the hell's a standard error? Well, the standard error is a measure of the variation in the sample means. Allow me to elaborate. I usually teach these concepts in earlier lectures during my stats courses. However, these quant concepts lectures are supposed to be self-contained, so I'll cover this concept here briefly. Now, suppose we have the population. The population includes every single observation in the entire world. In statistics, we usually assume the population is unobservable, as it is almost infinitely large. Now, suppose you're interested in the population mean. For example, suppose you're interested in the average height of men. I put a question mark next to the population mean, as it is highly likely to be unobservable to us. For example, it is very costly and time-consuming for us to measure the height of every single male in the human population, and then calculate the true population average. As such, we will never know the population average height of men. However, we can take a random sample of males, say 50 randomly selected men who by and large represent the population, and calculate the sample average. Seeing that this is a random sample and represents the population, then the sample average should be a good approximation of the population average. Now, suppose we take another random sample of 50 males and calculate the sample average for the second sample. The sample averages, x1 hat and x2 hat, should be quite close to each other as they are both representative of the population average. However, due to sampling variation and just randomness in the sample selection process, x1 hat and x2 hat, our two sample averages, are probably not exactly equal to one another. Similarly, imagine we did this another 3 times. So we take 3 random samples of 50 males and calculate the 3 sample averages. So we now have x3 hat, x4 hat, and x5 hat. Again, all the sample averages should be relatively close to one another as they all represent the same thing, the population mean. But due to sampling variation, they're probably not all exactly equal to one another. Now, the standard error is simply a measure of the variation across all these sample means. The formula for the standard error is this. Sigma, the numerator, is a population standard deviation, and n is the size of the samples. The intuition is this. The larger the population standard deviation, i.e., the more variation in the population, the more variation we will observe in the sample averages. And the larger the sample size, the smaller the variation in the sample averages, as there will be less sampling variation. In summary, the standard error is a measure of the variation in the sample means if you were to resample many times. Now, the next question is, why do we need the standard error in hypothesis testing? How is it relevant? Well, suppose we want to test the claim that the population average is equal to 100. We know the population is too large to be observed, so we take a random sample and calculate the sample average, and use this to inform us about the population mean. We calculate the sample mean, x hat, and we find that it is equal to 110. Now, the question is 110 sufficiently far from 100? That is, having found the sample mean that is 110, does this support or not support the claim that the population average is equal to 100? Well, this depends on the size of the standard error. The standard error is a standard unit of measure of the variation in sample means. If the standard error is equal to 20, then 110 is only half a standard error away from 100. This means that the sample mean is relatively close to 100, and that the population mean is likely to be equal to 100. If the standard error is equal to 2, then 110 is 5 standard errors away from 100. This means that the sample mean is pretty far from 100, and that the population mean is unlikely to be equal to 100. This is actually the essence of hypothesis testing. So whether the sample mean is close to or far from the population mean all depends on the size of the standard error. Alrighty, back to step 5. We need to calculate the critical value in the original distribution of sample means. Recall that the hypothesized population mean is 150. The standard deviation is 10, and the sample size is 30. And remember that the Z critical value tells us how many standard errors the critical value is below the hypothesized mean. The formula for the critical value is this. Notice that we have all the values, so we simply have to sub them in. The Z critical value, ZC, that we found from the Z-table is equal to negative 1.645. And we get 147. Pretty easy, huh? All we had to do was sub in some numbers. But what does this mean? Well, given our distribution and rejection region, we now know that the rejection region begins at 147. We compare this to the sample average that is given in the question, and see where it sits on the distribution. Since 120 is smaller than 147, the sample mean is in the rejection region. So this means we reject the claim that Sam's bowling average is equal to or above 150. The final step is to figure out whether we reject or don't reject the null hypothesis. This is the easiest step, so we're now in the clear. Since a sample mean falls in the rejection region, you reject the null hypothesis at the 5% significance level. Now, this is a very important rule. We only ever reject or not reject the null hypothesis. We never accept or reject the alternate hypothesis or accept the null hypothesis. Okay? So we always either reject or don't reject the null hypothesis. If we reject the null hypothesis, then we must conclude with the alternative hypothesis. Therefore, you conclude that Sam's bowling average is below 150. There, now we know, at the 5% significance level, that Sam is indeed lying. What does 5% mean? It means that there's a 5% chance we might be wrong, but we can live with that. Okay, I know this seems like it took a very long time to answer the question. It did, but that was because I was explaining in detail some basic concepts throughout the process. It's actually much quicker the more practice we get. Let me give you guys a summary of the steps involved, and we'll go through the remaining 2 examples relatively quickly. Step 1. Write down the hypotheses. We have to figure out which is the null and the alternate hypotheses and write them down in the proper format. Step 2. Write down everything you know from the question. What does a hypothesized population mean? The sample mean, the sample size, the significance level, and so on. Step 3. Draw the distribution of the sample mean and the rejection region. Step 4. Draw the standard normal distribution and find the Z critical value from the Z-table. Step 5. Calculate the critical value on the distribution of the sample mean. Step 6. See whether the sample mean lies in the rejection region or not, and reject or don't reject the null hypothesis. Then write down a conclusion to the question, such as Sam's bowling average is below 150 at the 5% significance level. Okay, so we're going to work through these steps systematically for the 2 remaining examples until we get the hang of it. Okay, example 2. Suppose Mike claims that the average price for houses in Castle Hill is more than $500,000. The population standard deviation of house prices is $200,000. You take a sample of 32 houses and find that the sample average house price is $530,000. Test whether Mike's claim is correct at the 1% significance level. Again, this is another exam question that I've used on my students many times, so it's good practice for your exams. Pop quiz. If our sample average for our 32 houses is $530,000, doesn't this mean the average house price in Castle Hill is above $500,000? That is, why do we even need to conduct hypothesis testing? Can't we just compare $530,000 with $500,000 and come up with a conclusion? That is, can't we just reject the null hypothesis now? Well, the answer is no. Why? Because the sample average of $530,000 may have occurred simply due to sampling variation. That is, it may have occurred purely due to randomness. Hypothesis testing allows us to figure out what's the probability that the sample mean occurred purely due to sampling variation. If the chance of this happening is less than the significance level, then the null hypothesis is rejected. In a nutshell, hypothesis testing allows us to account for the possibility of sampling variation, or randomness when sampling. Okay, back to our question. Step 1. Write down the hypotheses. This should be a piece of cake. Mike claims that the population average of house prices is above $500,000. Now, what is the counterclaim? Well, the complete opposite of this is that the population average house price is equal or below $500,000. The claim with the equal sign is a null hypothesis, H0. So the other claim must be the alternate hypothesis, H1. Rearranging these into the proper format with H0 above and H1 below, we get the following. And that's step 1 done. Pretty cruisy, yeah? One last thing. Notice that this is an upper tail test, as the alternate hypothesis has a larger than sign. Moving on to step 2. Write down everything you know from the question. We know that the hypothesized population mean, mu, is equal to 500,000. The sample mean of house prices is 530,000. The standard deviation of house prices is 200,000. The sample size n is equal to 32, and the significance level alpha is equal to 1%. Done and done. So step 3. We have to draw the distribution of the sample means, assuming the null hypothesis is correct. It looks like this, and assuming the null hypothesis is true, then the average of the sample means should equal to 500,000, which is a hypothesized population mean. Now, because this is an upper tail test, then the rejection region is on the upper side, or the right-hand side of the distribution. So the rejection region is here. We're told that the significance level is 1%, meaning that the rejection region contains the top 1% of the distribution. So far, so good. So the big question again is, what is a cutoff for the rejection region? What's the critical value? Step 4 is draw the standard normal distribution. We do this so we can find the critical value on the standard normal distribution. We use the Z-table to find the Z critical value. Once we know this, we can convert it back to our previous distribution of sample means. Okay, so we draw the standard normal distribution like so. Remember, it has a mean of 0 and a standard deviation of 1. The rejection region is in the same spot, as this is essentially the same distribution as in the previous slide, but it's just been converted into the standard normal distribution. So similarly, the rejection region contains 1% of the distribution. Again, the big question is, what's the Z critical value, or the cutoff value, for the rejection region? Now, recall that the cumulative Z-table gives us the area underneath the curve that is to the left of the Z value, which is this. What's the area of this region though? This is important as we need to look this up in the Z-table in order to retrieve the Z critical value. Well, we can use the complement rule. The total area underneath the curve must sum to 1. So the probability that Z is below a particular value is equal to 1 minus the probability that Z is above that value. So how can we use this rule? Well, 1 minus 1% is equal to 0.99. This means that the area we have to look up in the Z-table is 0.99 or 99%. Okay, so always remember that probabilities, or the area underneath the curve, must sum to 1. Let's take a look at the cumulative Z-table. So we need to find 0.99, which is here. We then find the corresponding row, and we get 2.3. Looking at the corresponding column, we find 3. So the Z value that corresponds to the cumulative probability of 0.99 is 2.33. So back to the distribution. So the critical value is 2.33. Too easy. Alrighty, so in step 5, we have to calculate the critical value in the distribution of the sample means, otherwise known as the original distribution. Now, how can we do this? Well, our Z critical value tells us that the critical value is 2.33 standard errors above the hypothesized mean. Because 2.33 is a positive number, it wasn't negative 2.33, then the critical value is above the mean, not below it. And recall that a standard error is equal to the standard deviation divided by the square root of the sample size. We have this information already. Remember, they were given in the question. The formula we use for the critical value is this. Note that we now know all the parameters needed. We know what mu is, the hypothesized population mean. We know what the Z critical value is. And we also know the population standard deviation and the sample size. So subbing all these values in looks like this. And we calculate the critical value to be equal to $582,378. Okay, so let's draw this in the original distribution. So we now know that the cutoff for the rejection region, or the critical value, is 582,378. So if the sample mean of house prices is above this number, then it falls in the rejection region. If the sample mean is below 582,378, then it falls outside the rejection region. Recall from the question that the sample average house price is $530,000. So this means it lies here. And as we can see, it is outside the rejection region. So step 6 is figuring out whether you reject or don't reject the null hypothesis. Since the sample mean was outside the rejection region, you don't reject the null hypothesis at the 1% level. Remember, we only ever reject or not reject the null hypothesis. Never say that you accept the null hypothesis. I get this all the time when marking exam papers. It's a very common mistake that can lose you some marks. Finally, it's always good to write a sentence concluding your findings. So you conclude that the average house price in Castle Hill is not above $500,000. And that's it. We've answered this question perfectly. Not too bad, huh? Once we get the hang of it, we can answer these questions much faster. It just takes practice. Okay, let's do example 3. We should be able to fly through this now. The average age of YouTube users is 25. You decide to test this claim using a random sample of 40 YouTube users. You find that the average age of your sample is 28. The standard deviation of the age of YouTube users is 15. use a significance level of 10%. Step 1 is to write down the hypotheses. This should be pretty easy for us now. So one of the claims is that the average age is equal to 25. So the counterclaim, the complete opposite of that, must be that the average age is not equal to 25. The claim with the equal sign is a null hypothesis, and the other claim without the equal sign must be the alternate hypothesis. Finally, we just have to write this in the proper format, and step 1 is done. Now, this is a two-tailed test. How do we know? Because the alternate hypothesis contains a not equal to sign. Okay, step 2. Write down everything we know from the question. First, we know that the hypothesized population average is equal to 25, so mu is equal to 25. We're also told that the sample average age, x hat, is equal to 28. The sample size, n, is equal to 40. The population standard deviation of the age of YouTube users, sigma, is equal to 15. The significance level of the test is 10%, so alpha is equal to 0.1. Finally, we can write up the distribution. Substituting the values in, we find that the sample mean will follow a normal distribution with an expected average of 25 and have a variance of 5.63. Okay, in step 3, we have to draw the distribution of the sample mean. We know it follows a normal distribution, like so, and that the hypothesized mean is 25. Because this is a two-tailed test, there are in fact two rejection regions. Now, in a two-tailed test, the rejection region is divided into two equal parts. What does this mean? Well, we're told that the significance level is 10%, so the total rejection region area must be 10%. By dividing this in two, we find that each rejection region contains 5% of the distribution. So the question again is, what are the cutoff values for the two rejection regions? We will call these the upper critical value and the lower critical value. Step 4 gets a little interesting here. We draw the standard normal distribution, and we do this so we can use a cumulative Z-table to find the Z critical values. Once we know the Z critical values, we can calculate the critical values in the previous slide. Okay, so this is a distribution in the standard normal distribution space. Notice that the mean is now 0. Now the question here is, what is the upper Z critical value and the lower Z critical value? This might look like we have to find two critical values, but in fact, we only have to find the value of one of them. Why is this? Because we can invoke the symmetry rule. The Z critical value for the lower rejection region is simply the Z critical value for the upper rejection region multiplied by -1. This is because the distribution is symmetrical around 0, like a mirror image. So the Z critical values actually look like this. So once we know one Z critical value, we know what the other one is. So we simply have to solve for one Z critical value. Now, remember that our Z-table is a cumulative table, so we need to refer to the area to the left of the Z value we're interested in. As the rejection region here is 5%, then the area to the left of this must be 95%. So it is this area of the curve we look up in the Z-table. Let's take a look at the Z-table. We need to find 95% or 0.95. Similar to the first example, we find 0.95053 here. However, 0.9495 is also just as close to 0.95. So we will use both numbers and take the average of their two critical values. Looking at the corresponding row, we get 1.6. The corresponding columns tells us that the second decimal places are 4 and 5. Taking the average of 1.64 and 1.65, we find that the Z critical value is equal to 1.645. Okay, so let's go back to our standard normal distribution. We've now figured out the value of this Z critical value. And using the symmetry rule, we know the lower Z critical value must be negative 1.645. So the upper Z critical value is 1.645, and the lower Z critical value is minus 1.645. Now that wasn't too scary, was it? Step 5. Calculate the critical values in the distribution of the sample mean. Now, the upper Z critical value tells us that the upper critical value is 1.645 standard errors above the hypothesized mean. It is above the mean as it is a positive number. The lower Z critical value tells us that the lower critical value is 1.645 standard errors below the hypothesized mean. How do we know this? Recall that the lower Z critical value is negative 1.645. Because it is a negative number, it is below the hypothesized mean. The formula for the upper critical value is this. We know what mu is, we know what the upper z critical value is, and we were given the standard deviation and sample size in the question. Subbing these values in gives us the following. So the upper critical value is 28.9 years old. Doing the same for the lower critical value, and we find that the lower critical value is 21.1 years old. Okay, time to insert our critical values in the original distribution of sample means. We now know that the upper critical value is 28.9 and the lower critical value is 21.1. It's the home stretch, we're almost there. Now, the sample average age of YouTube users was 28. This lies around here. Notice that this is outside the rejection region. Step 6. Do you reject or don't reject the null hypothesis? Well, you don't reject the null hypothesis at the 5% significance level. Why? Because the sample mean does not lie in the rejection region. Remember, we only ever reject or not reject the null hypothesis. These are your only two options. Therefore, you conclude that the average age of YouTube users is not statistically different from 25. Done and done. Hopefully, working through 3 examples thoroughly has given you a better understanding of hypothesis testing. As I've mentioned previously, practice is a key here. The method remains the same, you just have to get yourself familiar with it. Okay, a quick summary of what we've covered today. You should now know how to set up your null and alternate hypotheses. Remember, the null hypothesis is the one that contains the equal sign, and the alternate hypothesis is the other one. I covered 3 types of tests: lower-tailed, upper-tailed, and two-tailed tests. You can figure out which test is required based on the alternate hypothesis. I also talked about type 1 and type 2 errors. I covered the standard normal distribution. Remember, it is the same as the distribution of sample means, except that it's been standardized so it has a mean of 0 and a standard deviation of 1. We had to do this so we can refer to the Z-Table at the back of your textbook. I showed you guys how to use the Cumulative Z-Table and applied it throughout my examples. This is the most common Z-Table in textbooks. However, I also showed you how to use an alternate Z-Table if needed. Finally, I worked through 3 detailed examples of lower, upper, and two-tailed tests. Keep in mind, we used the critical value method. There are 2 other methods I'll show you in the next lecture. I used the critical value method today because it's the most intuitive method out of the 3. So what's next? The second lecture on hypothesis testing will cover a few more concepts and some more practice material to tie everything together. Specifically, I'll show you 2 alternative methods of answering hypothesis questions. These are the z-score and the p-value method. These 2 methods, along with the critical value method learnt today, will give us the same conclusions. However, sometimes exam questions may specify which method you have to use, and in some circumstances, one method may be easier to use than the others. I'll also go through the student t distribution. We will use this when we don't know the population standard deviation and must use the sample standard deviation instead. This is a more realistic application of hypothesis testing, as, in reality, we don't know the population standard deviation. I'll finish off with a brief discussion on the central limit theorem and how we have to be mindful of the sample size when conducting hypothesis testing. And that's it, guys. Thanks for listening to today's lecture and subscribing to Quant Concepts Education.